Namaste, my friend, and welcome back to JEE Chemistry with Typical Monk. This is Class 5, and today we arrive at the highest year chapter in the whole subject, chemical bonding. Here is a gentle mystery to hold for a moment. Water is bent. Ammonia is a squat little pyramid. Methane is a perfect, symmetric tetrahedron. 3 tiny molecules, 3 different shapes, and yet each one is built from the very same idea. When David first saw these shapes, he asked me how anyone could possibly know that water bends at an angle just under 105 degrees. And in G, this same idea also decides which bonds lean ionic and which lean covalent, and hides a lattice energy numerical inside a cycle named after Born and Haber. Today, one idea at a time, we learn how atoms bond, how to draw them on paper, and how one simple rule about repelling electron pairs predicts the shape of almost every molecule G can ask. Take a slow breath, let us begin. So what will you carry home from today's class? First, how atoms bond at all. Ionic versus covalent bonding, the octet rule that drives both, and Fajans rules, the G twist that blurs the line between them. Second, Lewis structures and formal charge, and the exceptions where the octet itself breaks down. Third, the heart of the class, VSEPR, how repelling electron pairs quietly decide the shape of a molecule. Fourth, the full shape gallery and its bond angles, from linear to octahedral, plus the single most tested picture in the chapter, lone pairs bending methane into ammonia into water. And fifth, the G drills, assertion and reason, match the column and how many are correct. So everything you learn today, you can also score with. Ready? One idea at a time. Let us start with the deepest question. Why do atoms bond in the first place? Atoms bond to reach a stable noble gas octet, 8 electrons in the outer shell, because that arrangement sits at lower energy, and nature always drifts toward lower energy. The first way there is the ionic bond, a complete transfer of electrons, usually metal to non-metal. Take sodium chloride. Sodium hands 1 electron to chlorine, and both walk away with a full octet. This bond is held together by lattice energy, and G loves to find that lattice energy indirectly through a loop called the Born-Haber cycle. Sublimation, ionization, and electron gain all added up using Hess's law. The second way is the covalent bond. Atoms do not give and take. They share electron pairs, as in methane and in water. And here is the G twist. Fajans rules. A small, highly charged cation sitting next to a large anion pulls even ionic bond toward covalent character. So, lithium chloride, with its small lithium cation, behaves more covalently than sodium chloride. The line between ionic and covalent is a slider, not a switch. Now we've reached the idea that quietly runs this entire chapter, BeCl₄, the valence shell electron pair repulsion theory. Watch the diagram grow. The whole theory rests on one sentence. Electron pairs around a central atom repel one another, so they spread as far apart as they possibly can. 2 pairs push to opposite ends for 180 degrees. 3 pairs spread to 120 degrees. 4 pairs open to 109.5 degrees. But the repulsions are not all equal. The order to memorize: lone pair on lone pair repels hardest, then lone pair on bond pair, and gentlest of all is bond pair on bond pair. That unequal push means lone pairs, being greedier for space, compress the bond angles. So here is the whole method in one breath. Count the electron domains, bonds plus lone pairs, around the central atom. That single count predicts both the shape and, as you will see next class, the hybridization. Now, let us draw what we just described. The Lewis structure, our way of bookkeeping electrons. The recipe: count the total valence electrons. Place the bonding pairs first, then spend the rest as lone pairs until every atom's octet is satisfied. When more than one drawing looks valid, formal charge is the judge. Formal charge equals the valence electrons of an atom, minus its lone pair electrons, minus half its bonding electrons. And the best structure is the one whose formal charges sit closest to 0. But the octet itself is not a law without exceptions. Beryllium chloride and boron trifluoride settle for an incomplete octet, while sulfur hexafluoride, phosphorus pentachloride, and chlorine trifluoride expand well past 8. Keep these 5 in your pocket. JEE tests them constantly. And when several good structures genuinely tie, we call that resonance. We unwrap it fully in Class 6. Let us walk the gallery of shapes, from the simplest to the most crowded. 2 electron domains give a linear molecule, beryllium chloride, stretched out at 180 degrees, sp hybridized. 3 domains give trigonal planar, boron trifluoride, at 120 degrees, sp² hybridized. 4 domains open into a tetrahedron, methane, at 109.5 degrees, sp³ hybridized. 5 domains reach the trigonal bipyramid, phosphorus pentachloride, with angles of 120 and 90 degrees, sp³d hybridized. And 6 domains close into an octahedron, sulfur hexafluoride, every angle 90 degrees, sp³d² hybridized. 5 shapes, 5 angles, 5 hybridizations, learn them as one family. Now, the single highest yield picture. In this chapter, watch what lone pairs do to a fixed geometry. All 3 molecules here have 4 electron domains, so all 3 share the same sp³ tetrahedral geometry underneath. Now methane has 0 lone pairs, so nothing crowds its bonds. It stays a perfect tetrahedron at 109.5 degrees. Ammonia has 1 lone pair. Pressing the 3 bonds closer, the molecule turns pyramidal and the angle shrinks to 107 degrees. Water has 2 lone pairs. Squeezing harder still, the molecule bends and the angle falls further to 104.5 degrees. Same geometry, same hybridization, 3 different shapes, because lone pairs, not atoms, are doing the pushing. Now sit up straight. These 5 lines are what JEE actually asks year after year. 1. The bond angle order. Methane at 109.5 degrees, greater than ammonia at 107, greater than water at 104.5. Memorize it cold. 2. More lone pairs mean a smaller bond angle. And remember, geometry is not shape. Geometry counts every domain. Shape ignores the lone pairs. 3. Learn the expanded octet shapes with their hybridization attached. Sulfur tetrafluoride is a seesaw. Chlorine trifluoride is T-shaped, both sp³d. Xenon tetrafluoride is square planar, and xenon difluoride is linear, both sp³d². 4. Fajans rules give you an order question for free. Covalent characterizes as the cation shrinks. So lithium chloride is more covalent than sodium chloride, which is more covalent than potassium chloride. 5. Carbon dioxide is linear and non-polar at 180 degrees, even though every bond in it is polar. Symmetry cancels the pull, and the same logic makes boron trifluoride non-polar too. Let us drill the JEE way. Remember the 4 options. Option A, both true and the reason explains the assertion. Option B, both true, but it doesn't explain. Option C, assertion true, reason false. Option D, assertion false, reason true. First, assertion. The bond angle of water is smaller than that of ammonia. Reason. Water has 2 lone pairs, while ammonia has only 1. Both statements are true, and the reason explains the assertion perfectly. Option A. Second, assertion. Carbon dioxide is a non-polar molecule. Reason. Carbon dioxide has polar carbon-oxygen bonds. Both true, no doubt, but the reason does not explain the assertion. Carbon dioxide is non-polar in spite of its polar bonds because its linear symmetry cancels them. Option B. Third, assertion. The shape of the sulfur hexafluoride molecule is octahedral. Reason. The central sulfur atom carries 1 lone pair. The assertion is true, but the reason is false. Sulfur hexafluoride has no lone pair at all. All 6 pairs are bonded. Option C. A quick match now. Say each shape aloud before I reveal it. Methane matches with tetrahedral at 109.5 degrees. Ammonia matches with pyramidal at 107 degrees. boron trifluoride matches with trigonal planar at 120 degrees, and xenon tetrafluoride matches with square planar at 90 degrees. If all four came to you before the reveal, the shapes are becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. Water has a smaller bond angle than methane. Hold your verdict. Statement 2. Lithium chloride is more ionic than potassium chloride. Think of Fajans before you decide. Statement 3. In VSEPR, lone pair on lone pair repulsion is the strongest of them all. So, how many are correct? 2. Statements 1 and 3. Water truly bends tighter than methane, and lone pair on lone pair repulsion truly is the strongest. But statement 2 falls. By Fajans' rules, the small lithium cation makes lithium chloride more covalent, not more ionic, than potassium chloride. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. Geometry and shape are just 2 words for the same thing. Truth. Shape counts only the bonded atoms. Geometry counts every electron domain. Ammonia and methane share the same tetrahedral geometry, yet one is pyramidal and the other tetrahedral. Myth 2. A bond between a metal and a non-metal is always purely ionic. Truth. Fajans' rules show that a small, highly charged cation, like the aluminium ion in aluminium chloride, pulls the bond firmly toward covalent character. Metal plus non-metal is not automatically ionic. Time to test yourself. Rapid fire. Here is the rule I ask, you answer in your head before the reveal. Question 1. What is the bond angle of water? 104.5 degrees. Question 2. What is the shape of methane? Tetrahedral. Question 3. Which repulsion is strongest in VSEPR? Lone pair on lone pair. Question 4. What is the shape of xenon tetrafluoride? Square planar. And question 5. The thinker. Which is more covalent? Lithium chloride or sodium chloride? By Fajans' rule, the smaller lithium cation wins. Lithium chloride. If you caught that, you have truly understood today's class. Let us gather the whole class in one slow breath. Atoms bond to reach a stable octet by transferring electrons in an ionic bond, held by lattice energy, or by sharing them in a covalent bond. And Fajans' rules remind us that line is a slider, not a switch. Lewis structures let us draw the electrons. Formal charge picks the best structure, and the octet itself has exceptions, incomplete and expanded. VSEPR is the master idea. Electron pairs repel and spread to maximum separation. The family of shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, each with its own hybridization. And lone pairs shrink the angles. Methane at 109.5 degrees, greater than ammonia at 107, greater than water at 104.5. And next class, we go deeper into the bond itself. Chemical bonding 2. Balance, bond theory and hybridization. From sp all the way to sp³d², plus resonance done in full. Do not miss it. And so, my friend, you have just built the foundation of the highest yield chapter in all of JEE Chemistry. One idea, electron pairs refusing to crowd, gave you 5 shapes, explained why water bends and methane doesn't, and even told you which ionic bonds secretly behave covalently. Sarah, David, Lisa, and John all began exactly where you are right now with this one class. Be patient with yourself. Tonight, redraw the 3 shapes once, slowly, and let the shrinking angle settle into memory. One idea at a time, you will crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you inside the world of hybridization.